Welcome to my classroom. This time, I would like to talk about the Fundamental Theorem of Calculus, which is expected to learn in M2. This theorem tells the relationship among the three branches of calculus, namely differentiation, indefinite integration, and definite integration. The theorem is included in the syllabus but not appear in exam papers. Students or even teachers might overlook the importance of the theorem. Mathematics originate from real-life problems. Let me start with a common discussion in physics. Suppose we are given a graph displacement against time for the movement of a particle. With the information of the graph, we can calculate the average velocity of the particle from the time t0 to t1. By definition, velocity is displacement over time. So, the average velocity is s1 minus s0 over t1 minus t0. If the function for the displacement is given by s equals to f of t, the average velocity is given by f of t1 minus f of t0 over t1 minus t0. Let us look at the geometric meaning of this fraction. In this right-angled triangle, opposite side over adjacent side gives the tangent of this angle, that is, the slope of line PQ. We know that the average velocity is an approximation. The instantaneous velocity of this particle in this region is probably different from the average velocity. Sometimes we need an accurate answer for the velocity, say the instantaneous velocity at the time t0. How to find it? What is the geometric interpretation? Let us introduce a variable delta t, a small increment of t. When delta t gets smaller, the average velocity gives a better approximate answer. As a limit, delta t approaches to 0. This fraction gives the exact value of the instantaneous velocity of the particle at time t0. Refer to the diagram. When delta t gets smaller, q gets closer to p. The line PQ approaches to the tangent at P. Thus, when limit is taken, this value is the slope of tangent to the curve at t equals t0. In mathematics, we put aside the physical meaning and just study the idea in an abstract way. So, very often, the discussion of differentiation starts with a function y equals to f of x and a value x equals a. The slope of tangent to the curve at x equals a is given by the limit. Denote this value by f prime a and call it as the derivative of f of x at x equals a. Generalize this result. Replace the specific value a by the variable x. We have the function f prime x, the derivative of fx. Here, the function f prime x equals the limit can also be denoted by dfx dx or simply dy dx. The very first method of getting the derivative by taking limit is called first principles. Using first principles, we derive properties and formulas to find the derivatives in a faster way. For example, suppose fx equals to 2x cubed plus 4. The derivative f prime x is 6x. This result can be derived by first principles, or it can be done quickly by using formula. The process of getting the derivative f prime x from the function f of x is called differentiation. Given fx, the process of finding f prime x or dfx dx is differentiation. The reverse process is called indefinite integration. To make the notation more natural, we use fx to stand for the given derivative and look for a function, say big fx, such that big F prime equals fx, or here we call this function big fx as a primitive function of small fx. Given fx, f prime x denotes the derivative, and big fx refers to a primitive function. The article tells the uniqueness of the functions. For a given function, its derivative is unique, but its primitive is not. A simple example can illustrate this. Suppose f of x equals x squared. Whether by first principles or formula, we have f prime x equals 2x, a unique result. To find big fx such that the big f x equals x squared, according to our experience of differentiation, we note this, and so as where c is any constant, that is, 1/3 x cubed plus c with any constant c can be an answer for big fx. Usually, we take the one without constant for the big fx. Thus, this is a primitive function. In general, we use the following notation to represent the relation between the function fx and its primitive big fx. The integral of fx is big fx plus c, where big fx is a primitive function of small fx and c denotes the integration constant. In textbook, after this definition and notation, we derive properties and formulas for indefinite integration from those results established in differentiation. Then, lots of practice are given for mastering the calculation techniques. Unlike the part of differentiation, we are not given much applications under indefinite integration, but spending more effort for the calculation techniques. Why we are so interested in finding the primitive functions? You can find the answer later. Let me start with a daily life example. Suppose the walking speed of a boy is 4 km per hour, and he walked for 3 hours. How far did he walk? It is simple. By the formula, distance equals speed times time. The distance traveled is 4 times 3, 12 km as the answer. Or we can visualize the solution by the travel graph, speed against time. The speed is 4 km per hour, a constant speed, so it is represented by a horizontal line in the graph. As the time taken is 3 hours, the distance traveled is given by the area of the rectangle with dimensions 4 by 3. Thus, the area 12 gives the distance traveled. From this simple example, we see that when the travel graph of speed against time is given, the distance traveled is the area of the region under the graph between the corresponding time slot. In general, suppose the speed of a moving particle is not constant, but a function of time. Say v equals f of t. The distance traveled by the particle from t1 to t2 is the area of the shaded region in the diagram. So, this example shows a practical reasons of finding the area of a non-rectilinear figure. Now, let us just focus on the question of how to find the area of a non-rectilinear figure, which is bounded between a curve y equals f of x and a horizontal line x-axis, and two vertical lines x equals a and x equals b as shown in the diagram. In junior forms, we learned the formulas of area of rectilinear figures. For example, we know how to get the area of rectangles. Let us use a number of rectangles for an approximate area. First, we divide the interval AB into a number of parts, say n equal parts. Then the length of each part is b minus a over n. Denote this length by delta x. which represents the width of a rectangle. Then select a sample point in each part for the height of the rectangle. To make calculation easy, we may select either right end or left end as the sample point. That is, with the width and height, the area of each rectangle is found. Add them up for an approximation. So we have, to make the approximation more accurate, divide the interval AB into more parts. That is, take a larger n. Take the limit of n to infinity. The exact value of the area is obtained when the limit exists. The area of the shaded region equals. German mathematician Riemann proved that both limits give the same value. In fact, so as all other choices taken in the interval. We call this calculation for the area as Riemann sum. In notation, we write, it is done by 4 main steps: partition, selection, summation, and taking limit. A simple example illustrates how the area is obtained by Riemann sum. First, partitioned, then selection, and summation. Finally, taking limit. That is, the definite integral is 1/2. In fact, the answer is expected. When we draw the graph, we see that this integral represents the area of the triangle whose base is 1 and height is 1, and thus the area is 1/2. From the above example, we can see that the working by Riemann sum is tedious. We want to find another way for calculating the definite integral. Also, we see that the indefinite integral gives a function and the definite integral gives a value. A function and a value are two different things, but the two integrals share very similar notation and terminology. Why? Are they related, and how? The answer is given by the Fundamental Theorem of Calculus. To find out the relation, we first change the definite integral from a value to a function. Consider the area function, a of t. We replace the upper limit of the definite integral by a variable t, so that the integral is in terms of t. As t is a variable, this expression represents a function of t. According to our discussion earlier, the expression gives the area of the region bounded by the function fx and the x-axis from x equals a to x equals t. So we call this as an area function. Since a of t is a function of t, we can differentiate the function with respect to t. By first principles, we see that the derivative of at is. Replace the functions by definite integrals. Apply the property of definite integrals. As delta t is tiny, the area is approximated by the area of rectangle. Take limits, the result is f of t. That is, the derivative of a of t is f of t. In other words, a of t is a primitive function of f of t. In fact, we can find another expression for a primitive function of f of t by indefinite integration, where big Ft is also a primitive function of small ft too. That is, the difference between at and ft is a constant. Replace the function a of t by the definite integral. We have, to fix the value of c, put t equals a. That is, to get the original definite integral, put t equals b. We have, the definite integral can be obtained without the tedious work by Riemann sum, but evaluate the corresponding indefinite integral at two limits and take the difference. This result is called the Fundamental Theorem of Calculus. It connects two different concepts, definite integration and indefinite integration, together. Let me put down the result of Fundamental Theorem of Calculus here. With the constraint of limited time in the video, I cannot include every details in the discussion. I expect you have learned this topic and some basic properties of calculus, so you can go through the video without difficulties. I produce videos on enrichment mathematics and try not to touch much on teaching syllabus. Those materials are supposed to learn well in classroom teaching. Yet, I notice many students or even teachers skip a proper learning or teaching on this theorem. Perhaps it may not affect the performance of doing exam papers, but you may miss a good understanding of calculus and see how two great mathematicians in 17th century, Newton and Leibniz, built up their ideas of differentiation, indefinite integration, and definite integration, and make calculation easy and possible. It laid a foundation for further developments in both mathematics and science, which led to huge development in technology thereafter. I believe this theorem is the most significant theorem we learn in secondary school level, and it is worth for our attention and appreciation.